We live in a world that's absolutely surrounded by invisible computers. They're in our cars, our banks, our hospitals, even in the planes flying miles above our heads. Now, for most of these systems, a simple crash isn't just an inconvenience, it could be a catastrophe. So, how do we build computers that simply cannot be allowed to fail? Well, that's the incredible world of fault-tolerant systems.
And this quote, wow, it really sets the stage, doesn't it? Every single time you get on a plane, or even just use an ATM, you're placing your trust in a massively complex system to perform flawlessly. The stakes just couldn't be any higher, which is exactly why this dedicated field of engineering exists, to manage that incredible responsibility. So for this breakdown, we're diving into a foundational text on the subject, fault-tolerant systems. You can think of this as the playbook for the engineers who build the bedrock of our entire modern digital world. Okay, so let's get right to the core of the problem. Computers are no longer just on our desks. They're critical components in everything from financial markets to medical equipment. A failure isn't just a blue screen of death anymore. It can have massive, real-world consequences. Now, what's really fascinating about this field is the mindset. Engineers in fault tolerance accept one fundamental truth: perfection is impossible. Every single system, whether it's hardware or software, has flaws. So the goal completely shifts from trying to build a system that never fails to building one that can survive its own inevitable imperfections. To manage failure, you first have to be able to talk about it with some real precision. And that art of anticipation, it all starts with a very specific vocabulary that breaks down the entire process of a system going wrong. It all begins with a fault. Now, a fault is the dormant flaw. It's the bug in the code that hasn't been triggered yet, or the hardware component that's slowly, quietly degrading. It's the potential for a problem, just waiting for the right conditions to show up. Next up, that fault can lead to an error. This is the moment the fault becomes active. That dormant bug gets triggered by some specific input, or that loose wire causes a voltage drop, leading to an incorrect value somewhere deep inside the system. An error is the very first sign that something is actually wrong. And finally, if an error isn't handled, it leads to a failure. This is the one we all see, the externally visible user-facing problem. The incorrect calculation causes the program to crash, or maybe the car's braking system to malfunction. So the whole point is this: fault-tolerant systems are designed to detect and correct errors before they can ever cause a failure. Engineers also have to plan for different kinds of faults. A permanent fault is like a burned-out light bulb. The component is gone, and it's not coming back. But the vast majority of faults are actually transient. Think of a bit of cosmic radiation from space flipping a single bit in memory. The fault happens, causes a quick error, and then poof, it's gone. Then you have intermittent faults, the most frustrating kind, which come and go like a loose wire, driving everyone crazy. So how do you fight back against all these different faults? Well, the primary weapon in the arsenal is redundancy. But it's not just about having a backup. It's a whole playbook of really clever strategies. The most straightforward approach is just good old hardware redundancy. If one component might fail, just have another one ready to go. It's simple, it's intuitive, and it's extremely effective. This illustrates a classic design called a pair and spare system, and it is brilliant. Imagine two processors doing the exact same job in perfect lockstep. The moment their results differ, even by a tiny bit, bam, an error is detected. The system doesn't even waste time figuring out which one is wrong. It just disconnects the entire pair and switches over to an identical spare pair with absolutely no interruption in service. But hey, you don't always need more physical hardware. Sometimes you can build that resilience right into the data itself. This is called information redundancy. The strategy is all about adding extra bits to your data in a mathematically clever way. These extra bits, they act like a built-in checking mechanism. Think about the RAID systems in data centers that can lose an entire hard drive without losing a single file, or the error-correcting codes that protect data being sent back from deep space probes. It's about being smarter, not just bigger. All right, our third strategy uses the dimension of time itself. Since most faults are transient, they just appear and disappear, sometimes the best solution is simply to wait a moment and try again. This is called time redundancy, and it's often as simple as an instruction retry. If a processor detects an error while doing a calculation, it just hits pause. It waits a few nanoseconds for, say, some random electromagnetic interference to pass, and then it simply executes the same instruction again. And for that huge number of transient faults, this simple retry is all you need.
Now, hardware is one thing. It wears out, it degrades, but software is completely different. A fault in software isn't a physical defect. It's a flaw in logic. It's a mistake baked right into the design itself.
And this question, this gets right to the heart of the problem. You can't just retry a logical bug. It's going to give you the same wrong answer every single time. And having two identical copies of flawed software doesn't help either. They'll just fail in the exact same way at the exact same time. This requires a completely different approach.
The solution is as radical as it is expensive. It's called N-version programming. You take the same set of requirements and give them to multiple completely separate teams. They each design, build, and test their own unique version of the software. The hope is that they won't all make the same mistakes.
But achieving that true independence is incredibly difficult. I mean, if the original specification is flawed, all the teams are going to build that flaw into their code. If one part of the problem is just intrinsically really hard, all the teams are likely to stumble right there. Even things like how programmers are trained to think can lead to similar mistakes. So the bottom line is, even with this method, these correlated failures are a huge persistent threat.
Okay, let's look at where these principles really come to life. These aren't just theoretical ideas. They are the absolute foundation for some of the most critical systems in the entire world. In aerospace, for things like fly-by-wire jets and deep space probes like Voyager, the name of the game is massive redundancy. We're talking multiple flight computers, multiple sensors, all heavily shielded to survive for decades in harsh environments. In contrast, you have NonStop servers, the kind used for financial transactions. They rely on a fail-fast principle. Every single component is constantly self-checking. The instant it detects an internal error, it just shuts itself down, allowing a backup to take over immediately before it can corrupt any data.
Finally, let's explore a more nuanced idea. Failure isn't always a binary on or off state. Sometimes a system can continue to provide a ton of value even when it's been damaged.
This is called graceful degradation. Imagine a complex satellite. Initially, it's at full functionality, everything's working great. Then maybe a solar panel fails. Okay, it can no longer run all of its science experiments, but it can still provide essential communication. It's entered a degraded mode. It might continue to lose capabilities as more components fail, but it's designed to cling to its core functions for as long as possible before ever reaching total failure.
And this brings us to a final, really thought-provoking question. The techniques we've talked about let us build systems of incredible complexity and reliability, but as we weave them ever deeper into the fabric of our society, we have to ask ourselves, are we creating true resilience, or are we just creating new and more sophisticated ways for things to fail? It's the central tension that's going to define engineering for the 21st century.